We're starting officially 1 minute late. So and I'm happy to introduce Anthony Genevois from Université X Marseille, who is going to talk about cubical-like geometry of graph products.
Thank you, and thank you for the invitation. So my talk deals with graph products, which are products of groups, and my goal will be to show that they act naturally on some spaces with a geometry which is not exactly cubical, but in the sense of quasi-cube complexes, but almost. And next, we will show how to use this geometry to prove some interesting results. So the first thing I have to do is to define graph products. So start with a graph gamma. Okay, so in all my talk, a graph is a simplified graph, so no multiple edges and no loops. Okay, and a collection G of groups of non-trivial groups. And labeled by the set of vertices of gamma. So I have just graph, and at each vertex I have group. Okay. Now I define the graph product in the following way. So just take the free product of all the vertex groups. Okay. And I had some relations to mean that two adjacent vertex groups will commute. Okay, so GNH commutes for every G in big G and every H in big H if G and H are adjacent. Okay, so to understand what happens, so it's interesting to look at the two following situations. So if gamma is complete, meaning that there is an edge between every two vertices, then everything commutes, and you get just the direct sums. Okay, and on the other hand, if gamma has no edges, then you have no relations, and you get just the free product. Okay. So if you have all the edges, everything commutes, and you have a direct sum. And if you have no edges, nothing commutes, and you have a free product. So, and graph products are everything between. Sometimes vertex groups commute, and sometimes not, and the commutation are encoded into the graph gamma, right? And there are classical examples of groups arising in this way. So if for every vertex group G is infinite cyclic, then this is just a right angle Latin groups. Okay. If every vertex group is cyclic over the 2, then the graph product is a right angle Coxeter group. Okay. And a very convenient property of these groups is that they have a natural generating set. And if you look at the Kelly graph, then this is naturally a quasi-cube complex. So you have a very nice geometry for these groups. But if you try to extend this observation to the graph products, then there are some difficulties. For instance, if you replace the Z mod 2 with Z mod 3, you will have triangles in the K graph, but in the one skeleton of a quasi-cube complex, you have no triangles. So the point is that it's maybe not a good idea to look for exactly a quasi-cube complex, and it is possible to find something which is just slightly different. So the proposition is the following. So I define X gamma G as a Kelly graph of my graph product with respect to the generating set, which is just the union of all the vertex groups. Okay, and I remove the identity to avoid loops in the graph. Okay, so this scalar graph is quasi-median. Okay, so here my generating set, of course, in general, it will be infinite. Okay, but it's not really important here. Okay, and now I will define what is a quasi-median graph, and I will show that this is essentially a quasi-cube complex. So definition: a graph say X is quasi-median if the following three conditions are satisfied. So the first one, for every vertices A, B, and C, suppose that you have such a configuration. So you suppose that B and C are adjacent, and you suppose that the distance between A and B is equal to the distance between A and C, say K. And if you have such a configuration, then there exists a fourth point, fourth vertex, which is adjacent to both B and C, and such that the distance between A and W is equal to K minus 1. Okay? So you can think of W as a kind of center of the three vertices A, B, and C. Okay? The second condition is similar. For every four vertices A, B, C, D, so you have something like that. So you suppose that C is adjacent to B and D, and that the distance between A and B is equal to the distance between A and D, say K. Okay, you suppose also that the distance between A and C is equal to K plus 1. Okay, so if you have such a configuration, then there exists a fifth vertex, W, which is adjacent to both B and D, and such that the distance between A and W is equal to K minus 1. Okay? So once again, this is a kind of center of the three vertices A, B, and D. Okay? And you have a last condition, is that the graphs, which are obtained by gluing two triangles along an edge or two squares along two consecutive edges, okay, so are not induced subgraph. So a subgraph is induced if when you take two vertices, they are adjacent in the subgraph if and only if they are adjacent in the whole graph. Okay? So in particular in a quasi-median graph, you can contain this graph as a subgraph, but if so, necessarily these two vertices must be adjacent. Okay? Okay, so this is the definition of a median graph, and to get example, for instance, look at a tree. Okay, a tree is a quasi-median graph, and in fact, as suggested by the terminology, quasi-median graphs generalize median graph. So a graph is median if and only if it is quasi-median and triangle free. So this is a proposition if you know what a median graph is, and otherwise you can take this as a definition. Okay, and the point is that a quasi-median graph is essentially a median graph in which you allow triangles. Okay, and on the other hand, a median graph is essentially a quasi-cube complex in the following meaning. So if you take a quasi-cube complex X, then you can produce a median graph just by looking at the one skeleton. Okay, and conversely, if you have a median graph, you can produce a cat-zero cube complex by filling in X. So what does it mean? You take your graph, and if you see the one skeleton of a cube of dimension n, you glue an n cube inside. Okay, and if you start with a median graph, you get the cube complex you obtain will be cat-zero. Okay, so the idea is just that quasi-median graphs are essentially cat-zero cube complexes in which you hollow triangles in the one skeleton. Okay, I should add some names here. So this correspondence was proved independently by Martin Roller in 1998 and by Victor Chepoï in 2000. And this definition was introduced in a paper written by Bandelt, Mulder and Wilkeit in 1994. Okay, so quasi-median graphs are not too different from cat-zero cube complexes, but what I want is that their geometries are similar. So what I will do is that I will define hyperplanes in quasi-median graphs, and I will show that the geometry essentially reduces to the combinatorics of the hyperplanes. So in a quasi-median graph, a hyperplane is a class of edges for the transitive closure of the following relation. So if you have a square, you say that the two opposite edges are equivalent. Okay, and if you have a triangle, then you say that the three edges are equivalent. Okay, and you take the transitive closure of this relation. I will give a concrete example in a minute. So first I will state the result on the behavior of the hyperplanes. So I fix a quasi-median graph X and a hyperplane. Okay, so the first point is that J separates X into at least two connected components called sector, and they are convex. Okay, the second point is that the subgraph n of J, n for neighborhood, of the subgraph n of J generated by J is isomorphic to a product. Okay, so C is a clique included in J. Maybe I should define a clique. A clique is just a maximal complete subgraph. So this is a maximal subset of vertices which are pairwise adjacent. Okay. So C is a clique, and F is a component of the complement. Okay, I will explain the statement in the following, in the next example. So the third point is that for every two vertices, so the distance between x and y is equal to the number of hyperplanes separating them. Okay, and the last one is that filling in x produces a cat-zero polyhedral complex. Okay, so you have something similar to this. The filling in a median graph produces a cat-zero cube complex, and CC it produces a cat-zero polyhedral complex. Okay, so I will write a precise example. So okay. Okay, so this is just the product of a triangle and a segment of length 2, right? Okay, so what are the, I claim that this is a quasi-median graph, okay? And what are the hyperplanes? So say that I start with these edges, and I want to determine the edges in the same class, right? So I have a triangle here, so all the edges are in the same class, okay? I have a square here, so the opposite edges must be equivalent. Okay, I have another triangle here, and similarly this triangle is in the class, and that's all. So in green, the green edges define a hyperplane in the quasi-median graph, right? And if I start with this edge, I have a square here, so I have this edge belongs to the class, and this edge also. Okay, and that's all. So this is a second hyperplane, and in white I have a third hyperplane. Okay. So the first point, the theorem is that a hyperplane separates into at least two components. So cutting along a hyperplane means that I remove the interiors of the edges. So if I cut along the green hyperplanes, I remove the interiors of the green edges, and I get three connected components: this one, and this one. Okay. And if I cut along the blue hyperplane, I get two connecting components: this triangle and this prism, right? And finally, similarly, if I cut along the right hyperplane, I get one triangle and one prism. Yeah. Okay.
So your graph is finite?
Not necessarily.
The number of components is finite?
So
Number of components is at least 2, but finite.
not necessarily. The number of components may be infinite. Yeah. And the second point is that if I look at the subgraph generated by the hyperplane, so I just take my hyperplane and I add the edges with endpoints inside my hyperplane, and this subgraph must be naturally a product. So if I take the blue hyperplane, okay, the subgraph generated is just the three blue edges and this triangle and this one. And it is a product of a clique inside the hyperplane, so this blue edge, and a connected component of the complement, say this triangle. Okay, so this works. Similarly, the neighborhood of the green hyperplane is the roll graph, and it is a product of a clique inside the hyperplane, so this green triangle and a connected component of the complement, right? And the third point is that the distance between two vertices is the number of hyperplanes which separate them. So if I take this vertex and this one, so the distance is 3, okay, 1, 2, 3, and I have 3 hyperplanes which separate x and y, the green, okay, the blue, and the right. Okay. And finally, the fourth point is clear in this example. Okay, you can naturally fill in the graph to get a cat zero space. Okay, just by taking the product of a triangle and segment of length 2. Okay. And the interesting point is that this statement almost word for word for cat zero cube complexes. The only difference is that a hyperplane separates into at least 2 connected components, okay, and maybe more. For instance, the green hyperplanes separates into 3 components, okay, and this is essentially this is the only difference. So the idea is that a quasi-median graph is a cat zero cube complex in which the hyperplanes separate maybe into infinitely many components. Okay, and the geometry is completely similar. We have a very precise dictionary between quasi-median graphs and cat zero cube complexes. And in some sense, it may be too similar because you can naturally associate a cat zero cube complex to any quasi-median graph in such a way that if you have a group with a good action on a quasi-median graph, then it has a good action on the associated cat zero cube complex. Okay, so the question now is, why is this graph interesting? So x gamma g, interesting. Okay, so I recall that x gamma g is the quasi-median graph on which the graph product acts. Okay, this is just the Kelly graph of with respect to the genetic set defining as a union of all the vertex groups. Okay.
So the distance is sometimes in 0.3, sometimes infinite.
No, the distance is always finite. Yeah, this is the distance is the graph. Oh yeah, so maybe I should add that x must be connected. Yeah, yeah. All my graph. No, maybe no. Okay, the graph x will be connected, and the graph gamma not necessarily. I should add this in the definition. Not here. Yeah, just. Okay, and condition 0 x connected. Okay. And okay, so the reason number 1 is that the geometry of the graph is easy to handle. So geometry easy to handle. Okay. In fact, we have a normal form for graph products. Okay, and this allows to give precise descriptions of the geodesics. Okay, and this is a good starting point to understand the geometry. And you can reprove using this quasi-median graph. You can reprove some known results on the geometry of graph products. For instance, you can determine precisely when it is hyperbolic, as defined by Kromov. And sometimes you can also improve these results, and it is possible to determine precisely when a graph product of finitely generated groups is relatively hyperbolic. But I don't want to say more about that, and I will focus on the reason number 2, which is a place where quasi-median graphs are the most powerful, I think, is that we obtain combination results. So this is a very natural question. When you have a product, the question is if all the factors satisfy some property, you want to determine whether the world group will satisfy also this property. Okay. So to illustrate the argument, I will consider the following results. So a graph product along a finite graph of cat-zero groups is cat-zero. So a group is cat-zero if it acts geometrically on some cat-zero space. Okay. So the assumption is that every vertex groups act geometrically on some cat-zero space, and the conclusion is that there exists another cat-zero space on which the roll graph product will act geometrically. Okay. So in particular, if we have to extend to start with a collection of actions and to produce an action of the roll graph product, and this is done by the following proposition. So for every vertex group, fix an action of G on some set X of G, okay, with a point of finite, with a point of trivial stabilizer. Okay. And the conclusion is that there exists a new quasi-median graph Y on which gamma G acts in such a way that for every click in Y, so this is a click, the action of the stabilizer, maybe this is, yeah, is isomorphic to some action of some vertex group G on X of G. So here isomorphic means that we have an isomorphism between the groups and a bijection between the spaces, which is equivariant with respect to this isomorphism. Okay? So this is the way to say that we have the same group acting on the same space and in the same way. And okay, so the idea of this result is the following. Okay, so I start with the quasi-median graph I have. So I take a click C in gamma X gamma G. Okay. Now the set of vertices of C is a set of elements of the group because I am looking at a K graph. And if you look at precisely, this is just a coset of a vertex group. Okay, so you have naturally a bijection with some vertex group G. On the other hand, you know that G acts on X of G with a point of trivial stabilizer. So if you look at the orbit map, you find an injection into X of G. Okay. So what I want is a quasi-median graph whose clicks are essentially copies of X of G. Okay. And here I know that X of gamma G is a quasi-median graph whose clicks are identified with subspaces of X of G. Okay? And the idea is just to add the missing points. So say that I have three clicks in x gamma g, which belong to the same hyperplane. Okay, then so as I said, a click here is naturally a subset of some x of g. Okay, and I add the points of x of g which does not belong to this subset. So say I add two points here, and now this will be the click of my new quasi-median graph. So I have to add an edge between every pair of points. Okay, so I have the same thing here. Okay, and I know that in a hyperplane I have a product structure, so I have to add these edges, and that's all. So this operation is inflating the hyperplanes of x gamma g. Okay, so I start with x gamma g. I inflate the hyperplanes using my collection of actions, and now I claim that this is a quasi-median graph, that the action on x gamma g extends to y and satisfies this condition. Okay, so the details are rather technical, but the basic idea is quite simple. Okay, and now I can sketch the proof of the theorem. Sketch of proof. Okay, so I start with the action of gamma g on x gamma g. So step 1 is to, so by assumption every vertex group acts geometrically on some K0 space. So I use this action to inflate the hyperplanes of x gamma g. Inflate the hyperplane of x gamma g, and you get an action of gamma g on a new quasi-median graph y. Okay, now the second step is to define a metric on the set of vertices of y. So in fact the goal will be to define a K0 metric on this space and to check that this action will be geometric. Okay, that's all. So how to define such a metric? So a good picture to have in mind is that the set of vertices of y is naturally a kind of cubical aggregate of copies of x of g's. So what does it mean? To produce a K0 cube complex, you take a collection of cubes, which are products of edges, and you glue them in a suitable way. Similarly, to produce quasi-median graphs, you take a union of prisms, which are products of clicks, and you glue them in a suitable way. But here, you know that each click of y is naturally a copy of some x of g's. Okay, so to construct a set of vertices of y, you can take a union of cubes, which are products of copies of x of g's, and you glue them in a suitable way. Okay, and using this picture is natural to define a metric on this set. So so the product metric on each cube. Okay, so this is not really a cube, but it's kind of cube. And next, you extend the metric. So you take 2 points of y. You take a path between them, which is in each cube a geodesic. And you define the length of this path as just the sum of the lengths in each cube. Okay? And the distance between x and y will be the infimum of the length of any length between these two points. Okay? So this is the natural way to define a metric on a polyhedral complex. Okay. Just a remark, this distance has nothing to do with the graph product on y. Yeah? I just use the graph product to see y as a union of kind of cubes. Okay? And the third step is to show that this metric space is cat 0. Okay? And the fourth step and last is to check that the action on y with this metric is geometric. Okay, and this concludes the proof. So I have other combination results, but the arguments follows always the same steps. The first step is to construct an action and quasi-median graph in such a way that on each click you have the structure. You have a structure. So here a cat 0 metric. Okay. The second step is to extend this collection of local structures to a global one. So if we have a global metric. Next, you study the global metrics, the global structure with respect to the local ones. Okay. So you see, you prove that the global metric will be cat 0. Okay, so the cat 0-ness in some sense extends from local to global, and the final step is to check that the action is the one you are looking for. Okay. Okay. Does it make sense? Right.
So what if you replace cat 0 space
What?
in the theorem with cat 0 cube complex?
This works. Instead of a metric, you can also extend a collection of walls. And you have essentially the same construction. Okay, so you have a collection. You have if you have a click, okay, you have a collection of walls on the click. Okay, and you have also a projection on each click. So yes, this is a click C. You have projection C, and for each wall you can extend as a for each wall in this click, you can produce a wall in the wall graph just by looking at the projection of some half space H, something like that.
But as a conclusion, you will have a polyhedral complex? Or?
Sorry?
As a conclusion, you will have the same conclusion. This is clear, but do you have something stronger? That if you make of cat 0 cubical, then you have, say, cat 0 polyhedral at the end.
On the space?
Yes.
Oh, to construct in this way, I get a quasi-median graph and a collection of walls on the quasi-median graph. And next I cubulate the wall space and I get a cat 0 cube complex.
Oh, so you have even, so if it is of cat 0 cubical, you get cat 0 cubical.
Yeah.
Yeah, that's what I was asking.
Yeah.
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 In fact, you are if every vertex group acts on somewhere on a cat 0 cube complex, say geometric or even properly discontinuous or even specially, then you can use this construction to produce the same kind of action for the roll graph product. Okay, on a cat 0 cube complex. So this kind of argument works for many situations. Okay. An interesting point is that in this proof, you do not really use the explicit construction of X gamma G. You just need to construct some convenient action on some quasi-median graph. So the question is that, is it possible to extend this argument for arbitrary group acting on some quasi-median graph? And the answer is yes. So combination results extend to arbitrary groups, acting nicely on quasi-median graph. So here I do not define what nicely means, because I will just say that this is a very restrictive definition, but it's interesting that there are many examples. So I will just give a list of examples of groups acting nicely in this meaning on quasi-median graph. Okay. So of course we have graph products. Okay, this is really the example where everything works and maybe in the most natural way. The second example, we have diagram products. Which were introduced by Guba and Sapir. Okay, so it would be really too long to give a precise definition, so I will just give some examples. So we have many graph products. Okay, so here this is not really interesting, but we also have some rest. We have the rest product with a copy of Z. We have something like a kind of bullet product, which is defined with the following relative presentation. So you take GH and some new generator T, and the relations are G commutes with H conjugated by T to the N for every N non-negative. Okay. So this commutator means that every element of G commutes with any element of this subgroup. Okay. You also have something like that. A, B, T, and A commutes with B and B conjugated by T. Okay. So you have many different kind of products, and in fact we do not know really what kind of product it's possible to obtain from diagram products, but you have a lot of examples. We also have rest products. G is H, where H is given with an action on some K0 cube complex. So of course the action of this rest product on the quasi-median graph we construct will be interesting only if the action on the K0 cube complex will be non-trivial. Okay. And last one, we have some graph of groups. Typically something like this. Okay, so vertex groups are products, direct products. Edge groups are factors, and the map are just the canonical one. Okay. Okay, but this last example is not completely written here, so I should hide some parentheses. so I have some time, so I will may give some details on the reason number 1. So I said that you can use the quasi-median graph x comma g to prove some results on the geometry of graph products. So if you look at the following example, so suppose that gamma is finite and that every vertex group is finite. So this is the situation where the generating set used to define x gamma g is finite. So this is really, so x gamma g will be really a geometric model for the graph product. Okay, and in particular, you know that if you look at the action on the K0 cube complex associated to the Cayley graph, the action will be geometric. So you already know that gamma g acts geometrically on some K0 cube complex. So this is a good point, okay? But you can, because you have an explicit geometry on x gamma g, you can use this action to prove more. So for example, you can prove that gamma g is hyperbolic if and only if gamma is square free. So no induced square inside gamma. Another result is that gamma g is virtually co-compact special. Okay, if you don't know what it means, you can forget this statement. And the last one, gamma g quasi-isometrically embed into a product of entries where n is equal to the chromatic number of gamma. Okay, so the statements are essentially already known, so I should mention some names. This result was proved by John Mayer. Okay, this was in 1996. This result was proved by Kim in 2012, and this one by Dranishnikov and Schroeder for right angle etc. Okay, so this is known, but you can use the same geometric model to prove all these results. And once you know some geometry and quasi-median graphs, this is not so difficult. So essentially, you just use some classical cubical geometry, okay, and you just use a dictionary between quasi-median graphs and cubical complexes to prove these results. And the results about so this result can be improved to detect relative hyperbolicity. So you can given gamma and g, you can define some collection of subgraphs I gamma g. This is a collection of subgraphs of gamma. Okay, and I don't define really this collection, but I just mentioned that it is easy to construct. Okay, on explicit examples. So, and statement is the following. So suppose that gamma is finite and that every vertex group is finitely generative. Okay. Then gamma G is relatively hyperbolic. If and only if. So relatively hyperbolic, I mean relatively hyperbolic with respect to some finite collection of subgroups, of proper subgroups. Okay. So if and only if the collection I gamma G is not reduced to just the roll graph gamma. Okay. And if so, gamma G is hyperbolic relatively to the subgraph product lambda G, okay, where lambda is an element of the collection. Okay. So you understand when the graph product is relatively hyperbolic, and if it is, you know with respect to which collection of subgroups it is. Okay. And okay, and I will stop here. Thank you for your attention.
Thank you very much. Other questions?
Sorry, is that I gamma? Is that just the cliques, or?
No, this is something more complicated. It is defined inductively. Okay, roughly speaking, you start with the squares in the graph gamma. So according to this results,
Oh yeah.
this is an obstruction to hyperbolicity. Okay, and if you have two squares such that the associated subgroups have an infinite intersection, then you put them together and you keep going inductively. And because gamma is finite, you have the process terminates, and this gives the collection I gamma G. Okay, this is not completely exactly this, but this is the idea.
Is the hyperbolic result equivalent to not containing Z cross Z?
Hyperbolic? Yes, yes. Hyperbolic, yes. This is exactly the statement.
Other questions? No, then we thank the speaker again.